A 5-hour clock, what we mean when we talk about a 5-hour clock, can be drawn like so. We've got the top of the clock, which is at 0, 1, 2, 3, 4. Each of these represents a passage of an hour, and we could certainly construct a 5-hour clock as opposed to the 12-hour clocks that we're used to. If we do this kind of arithmetic with a 12-hour clock, the kind of arithmetic we're going to develop here with a 12-hour clock, we would replace the 12 by a 0. And we'd have the numbers 1 through 11, and then 0 at the top. Now the question on a 5-hour clock, one of the first questions we could ask is, what would we get if we did some arithmetic on this clock? What would we mean by, let's say, 3 plus 4 on the 5-hour clock? Let's say we start at the top, and then we go 3 hours, so that's going to bring us around to the 3, and then we go 4 more, 1, 2, 3, 4 more. That's going to end up at the 2 o'clock position. So we're going to say that 3 plus 4 is congruent to 2 on a 5-hour clock. Now, the fact that it's a 5-hour clock will be represented by the mod 5 here. That 3 plus 4 is identical to 2 mod 5, meaning that on a 5-hour clock, adding 3 and then adding 4 more is equivalent to just going 2 units. And of course the reason for that is obvious. Now we're going to say that 7 is congruent to 2 mod 5, because on a 5-hour clock 7 gets us to the same place 2 does, because 7 and 2 differ by 5. So, if we go 7 hours on this clock, starting at 0, we end up here. The first 5 takes us around the clock once, and then the 2 that we have left over gives us the time, which is 2. We can also do multiplication on a 5-hour clock. We could do, let's say, 2 times 4 on a 5-hour clock. What would that correspond to? Well, that would correspond to going 4 and then going 4 again. 2 times 4 means 4 and 4. And we see that that gets us to 3. And we write that as 2 times 4 is congruent to 3 mod 5. Or 8 is congruent to 3 mod 5. We see again that 8 and 3 differ by a multiple of 5. That is, we go 8 hours here, well, we go 5 and then we have 3 left over. 3 is what's left over when we divide 8 by 5. We could do larger numbers. We could do 2 times 4 times 3, for example, is equivalent to what mod 5? Well, 2 times 4 times 3 is 8, times 3 is 24. On a 5-hour clock, if we go 24 hours, we'll go around 4 times, and then we'll have 4 left over. So we say that 24 is congruent to 4 mod 5. So that the number we have here is the remainder in the calculation 24 over 5. And again, the reasoning is simple, that if we went 24 hours starting from 0, we would go around here a certain number of times, and then we'd have a certain number left over, and it's the leftover number that tells us where we are on the clock. We can take this sort of arithmetic and we can write a table to represent the possible results. Our table here is going to be addition mod 5. The numbers are going to be 0, 1, 2, 3, 4. And the results that we get are going to give us a synopsis and maybe some kind of a picture of how addition works in these clocks. So if we add 0 to anything, well, that means that we start at the 0 and then we move either 0, 1, 2, 3, 4 units, and that's of course going to get us 0, 1, 2, 3, or 4. And if we move a certain number of units and then move 0 units, the same thing is going to happen. We're going to get 1, 2, 3, or 4. So that 0 plus 3 is 3, 4 plus 0 is 4, and so on, all the way down the table and across. Now if we add 1 to 0, of course we get 1. 1 and 1 gives us 2. 1 and 2 gives us 3. If we move 1 hour then 3 hours, we'll be at the 4th hour. And if we move 1 hour and then 4 hours, where are we going to be? We're going to be at the 5th hour, but there's no 5 on the clock. The 5th hour is taken by 0. The clock starts over again when we get to the 5th hour. If we do 2 and 1, of course that gives us 3. If we do 2 and 2, that gives us 4. 2 and 3 gives us 5. Now that means if we move 2 hours then 3 hours starting at 0, we end up at 0. And then 2 and 4, well, if we add 2 and 4 we get 6. If we go 2 hours then 4 hours, we will have gone 6 hours, but the thing starts over at the 5th. The remainder of 6 when you divide by 5 is 1. Then 3 and 1 makes 4. 3 and 2, of course, makes 5, which is represented by 0. 3 and 3 is 6, which puts us at the 1 o'clock position. 3 and 4 is 7, which is going to be the 2 o'clock position. And the table for 4 is constructed very similarly. And we can see a pattern emerging in this table. Let's zoom in just a little bit. Okay, we see how each row 0, 1, 2, 3, 4 goes. If we start 2, 3, 4, then we're going to go 0, 1. We're going to go back to the 0 and start over, because that's exactly what happens as you go around the clock. Note a couple of things here, that the first row, the one where we added 0, gives us the same numbers that we had in the table. And the first column, the one where we're adding numbers to 0, again, gives us the same numbers as there are in the column. That's an important property. That indicates that 0, when you're adding, doesn't change things. So that the 0 is the thing that doesn't change anything. We see that the 0 appears once in each row. Okay, 1 unit earlier each row. Starting here, then it's earlier in this row, and in this row, and in this row. And the reason for that should be obvious. You should think about that. Another thing we see is that every row is equal to the corresponding column. The row corresponding to 2 is the same as the column corresponding to 2. We got 2, 3, 4, 0, 1 here. We got 2, 3, 4, 0, 1 in the column. That's an indication or a result of the fact that it doesn't matter in which order we add two numbers. 2 and 3 gives us 0. 3 and 2 gives us 0. The 0 in this row corresponds to the 0 in this column. 2 and 4 gives us 1. 4 and 2 gives us 1. Because obviously the order of addition doesn't make any difference. Now let's quickly construct a table for multiplication. Mod 5. Now 0 times anything is going to give us 0, because if we go 4 hours 0 times, we haven't gone anywhere. Now whatever number of hours, if we do that no times, we get nowhere. Okay, 1 times anything means that we do whatever it is once. 1 times 3 is 3, because if we go 3 hours 1 time, we've gone 3 hours. Okay, 2 times 2, well, 2 2s is 4. That'll get us 4 hours in the clock. 2 3s is 6. 6 takes us to the 5 and around 1 more. 2 4s is 8. That ends up at the 3 position on this clock. And then 3 2s is 6, which is the 1 position. 3 3s is 9, which takes us around once and leaving 4 left over. Takes us to the 4 position. 3 4s is 12, which takes us around the clock twice with 2 left over. 4 2s, of course, is 8, which is 1 time around with 3 left over. 4 3s is 12, which we saw is 2. 4 4s is 16, which is going to take us 3 times around the clock, leaving us 1. This table also has some important characteristics. We see that this row is unchanged from the table, and this column is unchanged from the table. In both cases, it's because we've multiplied by 1. That's an important property, and we'll talk a little bit more about that. The zeros, of course, always give us 0. Another thing we can see is that, again, the rows and columns are identical, because the order of multiplication doesn't make any difference. We also see that every row and every column contains every number, and that's kind of an important characteristic.